Okay, today's date is January 6th, the year 2020. This is an update on the Gamma Drive project. The project itself was called Gamma Max, and the engine that is being developed is called the Gamma Drive. The Gamma Drive will have more than one cylinder when it's completed. At the present time, only one cylinder has been patented, and it's called an impulse driver. This is some of the information that's available at YouTube here. Okay, let's start off with the impulse driver. What does it look like, and where is it? Okay, here's the impulse driver as it was patented recently. Patent number 104-827-90. In this particular photograph, you see the gyro disc, and there's a thrust plate to the left of it, and at both ends there are stepper motors. The rest of the equipment is described in the patent, and I will be discussing it a little more here. Moving on. First of all, what makes this different, and why does it work under conditions that regular gyroscopes may not work? The idea of the gyro disc came about because of the limitations of a standard gyroscope as far as how it can be oriented, and some of the movements that were desirable could not be made with a standard gyroscope. In the upper left there you see a standard gyroscope that I think everyone here at the website will be familiar with. To convert it into a gyro disc, the first thing you want to do, get rid of the frame and get rid of the bottom half of the spindle. It's not needed. The essential part of gyroscope, especially for inertial propulsion, is just the rotor. So in image B we see the bottom half gone, the frame is gone, and temporarily the spindle itself is gone because we need to have two halves to the one spindle. In the lower left you see the parts of a gyro disc. I color the two halves different colors, and it makes it easier to identify some of the motions that's going on when it's running and videotaping. So there you see the two halves. You still have the rotor, and now instead of just a skinny spindle stick we have a more stronger rotor support, and then you have the axle, and the axle now goes through a much wider spindle that we replaced the skinny one that is with a standard gyroscope. So now we have a spindle that the gyroscope can be rotated about, and we have the axle which the gyro can be pivoted on. Let's go further here. So, what do we do with it? And let me zoom in a bit. Well, I'll keep it like this for now because other images are coming up. What we have here is the bottom of the test stand, and this is just a regular load cell scale that was bought at the drugstore actually. And I went in and tapped into the electronics for the load cell itself, and you see the bottom part of the impulse driver here. So it's sitting down on the load scale. These aluminum T-bars are guide bars which are described in some of the other videos on my website. Takes a minute here to get back to where I was at. Okay, here we are. Yeah, I guess I should have rehearsed, but I think you'll still appreciate the information that's available here. Let's take a look at test number 76, which is just a snippet of information about one of the tests. Hello. Okay, here we have it. And GM is just gamma max for the test sequence. All the information I'm presenting to you, almost all of it, is from the gamma max testing, which went on basically since 2007. So in test number 76, we see what's a typical DATAC data recording plot. And just a little background about this. I use 6 channels. The top channel is for acceleration. There's an accelerometer in the impulse driver. The next channel 2 is the upper motor. There are 2 motors like I showed you earlier. The upper motor is used to rotate the gyro disc. The third channel is the lower motor. The lower motor creates a, you can call it a centrifugal field that the gyro disc gyrates in. It's not really centrifugal force, but it's easier to think about it that way than angular momentum at this point. Channel 4 is just a marker pulse which flashes a light into the video stream so that we can synchronize the data here with what you would see on a video test. And channel 5 is the pivot encoder, which is one of the latest improvements of the device. The pivot encoder is just that. It monitors the angle of pivot of the gyro disc and sends signals to the computer as the index goes past and so forth. It's described in the patent. And then channel 6 is actually this channel from the load cell scale. And the important thing to notice here, I zoomed in, the gaps that you see here is more or less at these earlier tests. I was turning the motor on and off, varying the speeds of the motor and so on to get different information rather than to just run it for a long time with one set of parameters. So I decided to take this snippet here and blow it up for you. And what we're seeing here is the actual weight of the impulse driver down on the scale. And the background is here. The point being, before the impulse driver was loaded down on the scale, the reading was up here as far as weight, and then we see the weight of the engine. It's moved around manually a little bit, and then once the test starts, there's no gamma effect, no oscillating of the gyro disc in its preferred method until this point here. And at this point, which you may not be able to see so well, just get down here for you. Okay, at this point here, the gyro disc has reached resonance speeds and it starts oscillating in the preferred manner. So we zoom up here and we can see the baseline, which is just the weight of the impulse driver when it's sitting in a static mode, not running. And here you see that it got lighter in weight, clearly. And if you do all the numbers and whatnot, it ends up being approximately 5 newtons of reduced weight. Okay, let's pull back here so you can see more of this. Okay, can't really pull back, so I'll zoom around for you. The different channels. Okay, coming right along here, take a look at the motors. No big deal here, it's just that the speed of the upper and lower motors are monitored on the scope and recorded. Gives us a very clear indication of the speed in hertz, upper motor and lower motor. This information was gathered, of course, in real time. And then after a long time of experimenting, we get to a classic pulse. I've been doing tests to isolate what a classic pulse looks like. Just an individual one-time pulse. I've run many tests now and I've identified this. Basically this is used for processing. Once we detect the index pulse, we know the orientation of the two stepper motors already, and now we know the orientation of the gamma, the gyro disc, and from there we can control the amount of force by synchronizing these classic pulses. Give the system enough time for the pulse to run all the way through and then initiate another pulse. Over here is just a shot of the orientation of the disc before it begins. Because I use stepper motors, I can positively repeat tests as far as positioning. In earlier tests without the pivot encoder and without stepper motors, the results of the test varied greatly, and it was determined that the starting positions for this device is critical. Okay, moving right along. Once we got things figured out as far as the pivot encoder controlling the motors, things got a lot smoother. I'm not showing the pivot encoder pulses during this video. I guess you can say that's still classified. Anyway, this is test 99, and again the channels are the same as before. Acceleration up top, upper motor, lower motor, and I didn't show the marker pulses. That's not important, but you can see now that the modulation of the weight of the engine is much more steady down at the bottom there, and that's what we want to do. We want to increase the power with resonance. Resonance is the speed ranges where the gamma effect is apparent. I guess the scientific term is parametric resonance. And what else do we have here? Then we have the plots that I want to show you. Okay, and again I apologize for everything not being in view at once, but actually it turns out the resolution is so bad you might not be able to read anything I'm trying to show if I zoom back. So now at test 100, you can see the acceleration pulses, which are dramatically stronger than previously and above their baseline. Each of the signals has a baseline, and we can tell the direction of forces by the polarity of the signal here on the plot. You can see the upper signals. Lower motor signals are so bunched up because of the speed. I think we're running at 16 to 1 here. There's the marker pulses, and then what I'm really getting at here is I want to bring this all around to how many newtons of lift are we getting. And I think that's the important thing that most of the gyronauts will want to know. If we look across the bottom part of the plot here where the weight is showing, we see 4 separate snippets of tests, and what we want to do is measure the positive or upward. We want to average the upward energy that makes the device lighter, and we need to reference that to a baseline. The baseline, as I mentioned before, is the weight of the engine when it's basically turned off but sitting on the scale, and we can see that value over here on the left. Okay, my cursor disappears on this graph. So on the left there, you see the baseline value, and it turns out that during the test the baseline value does shift somewhat. It drifts over to here. So when I'm doing the math, I take the average of the baseline. Actually, I take quarters of the baseline, not just the average. And we're going to look at 4 separate zoomed in versions of this image. Okay, here we go. You saw in the previous image there were 4 different sections, and here we have each of them. So section 1, 2, 3, and 4. If you pause this video and look at each one, you'll see that the y-axis scale is identical. And it turns out that the numbers are that the baseline value is actually 6 to the minus 1. 6 to the minus 1 on all 4. That's the baseline, remember. The weight of the engine when it's just sitting still and powered down. And what you're seeing is only the positive pulses above that when the engine is getting lighter because of its running. And the average of the pulses that you're seeing here, minus the baseline, gives us a voltage value for the lift that's occurring. And just by looking at the calibrated chart for the load scale, we're able to interpret all that into newtons of force. And for this particular test, GM100, it ran approximately 10 newtons, 9.5 newtons of upward force, net upward force. And let's go back to a classic image here. Of GM34. This image is, well, this particular image is not in the patent, but this is channel 1 only of the tests of GM034. This was the first time that the engine in a counterweight mode, not down on the scale, but with the counterweight as described in the patent, rose all the way up to its stopping point. And I don't have the actual quantitative values here, because the point I'm trying to make can clearly be seen by the baseline value here and the upward acceleration. We're not looking at force here from the load scale. We're looking at accelerator signal. So it's very clear that the upward acceleration is far greater than the lower acceleration. Okay. And we'll take a look at a little history. This is all the way back to 1992. This was an earlier Gamma 910 model, and the upper motor, lower motor, instead of the base plate as described in the patent, there's a swivel arm here. It still performs exactly the same function, which is to give us a radial distance here for the spindle. And there's a thrust plate. For those of you that have been on the gyroscope.org website, you may recall Ravi talked about the J parameter and how a gyroscope could be made to hit a thrust plate and perhaps generate some lift. I wasn't able to generate lift with this design. In this picture you don't see the gyro disc, but the gyro disc configuration has never changed. The weight of the gyro disc has changed. Different materials have been used: aluminum, steel, and brass. And then our last picture is just the proud papa. It's like I've given birth to a child here. Finally, after battling with the patent office for quite a while, I did get the patent. So we're moving ahead now. One of the local colleges has showed some interest in giving me some space to work there. Since the patent is titled a teaching aid for teaching the principles of an impulse driver, it would be very beneficial to have a college or school do some training with the device just to verify its usefulness and its patented utility. Of course, from a propulsion standpoint, I'm moving towards the gamma drive engine. And that's my story. Thank you for watching, and if you're interested, you can respond to this video at www.gyroscopes.org.